Hello and welcome to Nerdy Nisa. Today we're going to be practicing how to prove different trig identities. We're going to be using the same steps that we talked about in the previous video, so I would recommend watching it because we're going to be referencing some things that were discussed there. We're going to start off with some easier examples and then work our way to some more trickier ones. So let's look at the first example. Before we do this example, I do recommend that you pause the video just so you can practice this by yourself first. Lovely. Let's then look at it. We've got cos squared y minus sine squared y is equal to 1 minus 2 sine squared y. Everything's already in terms of sine and cos, so that's the first step pretty much done for us. Lovely stuff. Let's then look at it. What do we want to achieve? We want to 1 minus 2 sine squared y. Now that 2 sine squared y is pretty much the only place that we see a ratio. So we've only got sines on this right-hand side. That means that the problem on our left-hand side and the thing that we need to fix is this cos. We need to oust it out of there because we don't want it in our final answer. Now, let's think of it. What kind of identity can we link sine squared and cos squared together so that we can get rid of this cos squared y? Well, I know an identity that goes sine squared y plus cos squared y is equal to 1. If I rearrange this, I can say that cos squared y is equal to 1 minus sine squared y. Now what I can do is take that answer and sub it in. So take what cos squared y is equal to and sub it in to where I see cos squared y in my expression. Well, in my equation, rather. Lovely. So let's do that. Let's then say that it's 1 minus sine squared y minus sine squared y. And if I were to simplify that expression, I'm then going to get 1 minus 2 sine squared y. Bada bing, bada boom, we've proven the identity. Let's look at the second example. Here I would also recommend that you pause the video just so you can attempt this one by yourself. This one here says sec squared theta over sec squared theta minus 1 is meant to equal cosec squared theta. Yeah, this says cosec over here. It's just written in shorthand. I do apologize for that, but that's cosec theta over there. Cool. The first thing we're going to want to do is get rid of all that cosec, sec, cot, all of that nonsense, because we like working in sine, cos, and tan, and so that's just all a bit confusing. So what I would recommend doing is converting that sec squared theta to 1 over cos squared theta, and you can put that over my 1 over cos squared theta minus 1, because now I've replaced all my sec squared thetas on my left-hand side with 1 over cos squared theta. Now, if I look on my right-hand side, that cosec squared theta is equal to 1 over sine squared theta. So there we are. That's essentially the type of equation that we're working with and that we're going to try and remodel. Now, when looking at this, there are two different ways that you could approach it. So this is where I would use that mind map method, just so you can branch it out and just kind of explore the different ways before you do it in pen, just to see which one's easiest for you to pick. So for the first way, this is if you've really studied your identities well, and you can already recognize that the bottom here, the bottom denominator, so that 1 over cos squared theta minus 1, that actually forms into one of the identities we were talking about. That identity that goes 1 plus tan squared theta is equal to 1 over cos squared theta can be rearranged to give us tan squared theta is equal to 1 over cos squared theta minus 1. So I can actually sub that tan squared theta into my denominator, and I can end up with 1 over cos squared theta all over tan squared theta. Alright, so that's a way that I could start remodeling it, and this is going to take me on a different path. So now I don't like this complex fraction thingy-majig, so I'm going to want to try and multiply it out. So I can multiply this whole thing by a fraction that's cos squared theta over cos squared theta, because cos squared theta over cos squared theta is going to give us 1. So if I multiply it by that 1, it's not actually going to change the value of my fraction, it's just going to help me remodel it. So if I take this and I multiply it inside my fraction, that's going to give me 1 at the numerator, because 1 over cos squared theta times by cos squared theta is going to give me 1. And then it's going to give me tan squared theta times cos squared theta at the denominator. So I'm going to write that out nicely, cos squared theta at the bottom. And then that's then equal to the final thing that we were talking about and the final thing we want to remodel our right-hand side to, which is that 1 over sine squared theta. And the way that I do this is by using the exact same triangle that we talked about before. That triangle that tells us if I've got a sine theta at the top and I've got two cos theta and a tan theta at the bottom, that means that cos theta times tan theta is going to give me a sine theta. The same is true for their squares. So over here, I've now proven that the left-hand side is equal to 1 over sine squared theta, but to just properly end it off and get it exactly how the question gave it to us, you can then finally say that that's equal to cosec squared theta. But let's say that you didn't see that you could just use that identity, because maybe you just don't know those identities as fluently. That's okay. There are still other ways that you could remodel this. So an alternative path that you could take is you could try and multiply out the denominator from the get-go. So I could take this fraction that I have here, that 1 over cos squared theta, over 1 over cos squared theta minus 1. I could take all of that and I could multiply it by a similar fraction of cos squared theta over cos squared theta. So it doesn't change the value of it, but it helps us get rid of these denominators within our fraction, just so we're not working with a complex fraction anymore. That's going to give me 1, because I'm going to have 1 in my numerator as 1 over cos squared theta times cos squared theta is equal to 1. And then in my denominator, I'm going to have 1 minus cos squared theta. And the reason I have that is because I'm going to take that cos squared theta, times it by this first fraction, which will give me 1, and take it and times it by the second term over here, which is 1. So that's 1 times cos squared theta, which gives us cos squared theta. Now if I've got this fraction, I then know one of my identities tells me that if I have a sine squared theta, that's equal to 1 minus cos squared theta. Therefore, I can sub in sine squared theta into that denominator. That's going to give me 1 over sine squared theta, which then once again gives me cosec squared theta. Let's look at this next example. It says tan squared x times sine squared x equals to tan squared x minus sine squared x. I do recommend that you pause the video here so that you can attempt this question on your own. Lovely. So now when I'm looking at this, there aren't any big glaring ratio issues. Like there's no big ratio that seems out of place like tan, and on the right hand side you've got tan and sine, and on the left hand side you've also got tan and sine. So ratios don't seem to be my biggest problem. So now this is going to require a bit of fiddling around, right? I've got a tan squared x and a sine squared x that I can work with. So let's divide it into 3 different parts that I could take. This is a big mind map method. This is when you're really just kind of guessing in a test, right? So you want to just do 3 different methods in pencil. Once you get the hang of proving trig identities, you can see which methods you're not even going to try to pursue. But if you're still a little new to this, you might try and pursue all of them. So the first method that I'm going to try and pursue is just kind of sub into my tan squared x. So I can say that tan squared x is the exact same as saying 1 over cos squared x minus 1. And I want to times that by sine squared x. Right, that's the first option I have. The second option I have is I have something where I could sub into my sine squared x. So what's a ratio that I know that could, or at least a trig identity that I know that could relate sine squared x to something? I know that I could sub in something like 1 minus cos squared x then. And that would all be timesed by my tan squared x. And then the last method that I could probably think of kind of branches out into 2 different ones. And that's the method where I'm using the ratios from my triangle. So my tan squared x could become something like sine squared x over cos squared x. And that would be multiplied by my sine squared x. And my other way I could do this is by changing my sine squared x to tan squared x times cos squared x. So that would give me my tan squared x times by my tan squared x times by my cos squared x. So here I've got a bunch of different ways that I can approach this, but let's just look at them for a little bit and see which ones are probably going to be the simplest and help us the most, right? So if I'm looking at this, I can see that this one looks like it's going to get a bit tricky, because what this is going to do is it's going to make everything a fraction. Then I'm going to try and have to scale down the fraction. And the problem with this one is it doesn't even have a minus sign within it. So it's definitely not an option that we're going to want to consider, because if there's no minus sign and I'm going to have to scale down a fraction, it's not something we want to use. For this one over here, also, similar problem. I mean, we don't have a fraction, but there's no minus sign. So I don't know how that minus sign is just going to appear if I use this branch. So it's also going to be way too complex, not a method that I want to pursue. Now I've got these two methods available to me. They both have minus signs. This one does have a fraction, but I feel like let's just give them both a shot. Because, I mean, the fraction is the only thing that's playing this one down. So let's just be a bit kind. Let's just follow them to at least the next step so that we can assess them. If I take the purple one to the next step, I can multiply in that sine squared x into that 1 over cos squared x minus 1 bracket. Lovely. So if I multiply that in, I'm going to get sine squared x over cos squared x minus sine squared x. And then if I take my pink path to the next level, I'm going to get tan squared x minus tan squared x times cos squared x. Oh my golly goodness. And would you look at that? This one is definitely the path that we're going to be wanting to follow, because I can already see that tan squared x times cos squared x is going to give me my sine squared x. So then from here, I can immediately say that's equal to tan squared x minus sine squared x, and bada bing bada boom, my identity is proven. Now, if you had stuck to the purple path, you might also have recognized that on both sides, you can actually pretty easily get to the final result. Because on this purple side, that sine squared x over cos squared x is going to also give me tan squared x. And then that minus sine squared x is equal to my identity. So both paths would actually be valid. So both my purple path and my pink path are both valid ventures. They're just that they would take different ratio conversions and they would use different identities. But the yellow path was definitely easy to eliminate because you don't even have a minus sign, so I don't know how that would then appear. Thank you so much for watching this video. I hope that it really helped. If not, and you have any questions, please leave them in the comment section below, and I'll try and help as best as I can.